All right, so here in this video, we're going to look at languages, right? In the at least in a mathematical sense. Our goal here is for this section and leading into the next section really, but here in this section is just to define what a language is in a mathematical sense, and our goal here is to use that to describe or define what the DFAs, what's called a deterministic finite automation. So what something a way to recognize, right, patterns within strings, right? Now the idea is, what is a language, right? Now English is a language in like our everyday language. C++, right, is a set of valid programs, right? URLs are a set of valid web address. Now when we talk about formal language theory, excuse me, all of these are sets of strings, right? So we will make this precise and use it to build machines to recognize membership in these sets, right? So here, this video itself will be very vocab forward, right, to just get us comfortable talking about languages in this particular context of DFAs. All right. Now, an alphabet. So here we're going to define this Greek letter sigma, and this is when we use the letter sigma, we're referring to an alphabet. Okay, and so this is a finite non-empty set, and the elements here are called symbols. So here, alphabet, finite, non-empty. So it has at least one member. Non-empty set, right? And the elements are called symbols. So here, okay, so the elements are called symbols here. So some examples here, we can think of binary, right? So examples of alphabets. 0, 1, right? 0, 1, the digits through 9, the ASCII character set. Right. So those are some examples of some alphabets. Now, we could say a string over sigma over an alphabet is a finite sequence of symbols, right? So string over an alphabet, right, is a finite sequence of symbols. So again, so what that means here is that, right, since it is a sequence, then the order matters here. So if we're dealing with the 0, 1, right, this is different than they're both strings, right, with two ones here, but since it is a sequence here, then the order does matter here. Right, so this is a string over the alphabet 0, 1 here. The empty string denoted by the letter epsilon has no symbols. Right, and length 0. Okay, so here, some operations we want to find over strings, right? So we want to classify, right, string operations. First one is length, right, which we define x. If x is our string here, then the length of it is this is a symbol for finding the length of substring x, right? So x is some string. Using a notice here that the absolute value in this context, we're talking about strings, gives us the length, right? So here, if let's say our x was 0, 1, 1, right? The length of x is 3, right? The length of the string, how many symbols, right? So that's one operation. The other one is what's called concatenation. Right, so that looks like, let's say if x was 1, 1, 1, y is 0, 1, 0, right? Then we define this here to be I just kind of put them right next to each other. Okay? All right, now keep in mind here that this is not the same as yx. All right? Okay, so xy cannot be assumed to be the same as yx. In other words, it's not commutative. Okay, so we also have a reversal of a string. Right, notice defined by xr, right? So if x, we take the xr, yeah, actually, let x, okay, let's say x was defined as this, then xr would be this, right? You just reverse it. Okay, all right, so those are some operations of strings. Now, we define this set, sigma star, right, is the set of all strings. All right, so the set of all strings over the alphabet, over E, right? And this includes epsilon. Okay, so similar to like our set theory, right? When dealing with sets, the empty set is a subset of any set. So here the empty string is a subset of E star. That is a string, right? So here it is a string. We classify the length of E to be of length 0, right? But it is a string. All right, now this set E star is always infinite, even if our sigma, our alphabet, only has one symbol. So here, just E star is infinite. Okay. All right. Now, a language over any alphabet is any subset of E, right? So a language, say that one more time. Language over an alphabet, right, is any subset of E star. Okay. All right, now languages can be finite or infinite, right? So here are some examples here that our textbook cites here. So we can think of an example here, L1 to be so for this is finite, L2 to be 0, 1, 0, 1, 1, 0, 1, 0, and see we can, we can build a pattern like this and build a set like this, and we can see building it like this, we have this to be infinite. Have L3. Here we have, if x is an element of sigma star, then n0 of x equals to n1 of x. Right? And this is equal number of zeros and ones, right? Which can also be infinite, right? Just a different way besides kind of listing out the elements, different way to define a set or a language, right? So one thing to keep in mind here in kind of all this talk that we've had here, language is we're purely talking about a mathematical object, a set of strings, right? We're not talking about grammar, no meaning, just a set and the membership in the set, okay? Language operations, we can have other operations like union, intersection, complement, but all these are always relative to our sigma star. Okay, so concatenation and something called the clean star are all strings formed by concatenating zeros or more strings from S, right? So again, all that means is that unions, intersections, and complements are always relative to our overall set sigma star, right? Which again is the set of all strings over the alphabet. Okay? All right, so one thing to notice, or one thing to kind of realize here, is that E star is infinite, but it's what's called countably infinite. And what that means is that you can put it in a one-to-one correspondence with integers, right? So you can count them in a sense like naming them out like 1, 2, 3, even though that goes up to infinity, but you can put it in that, you can establish an order in that way or a relationship in that way. Okay? All right. As opposed to if you think of the real numbers, right, even within just a subset between 0 and 1, right, we can't really put those in, we can't really count those, right? There's what's called uncountable, right? So it's a different kind of infinite set, right? So an uncountable infinite set. But for our purposes here, countably infinite, all right? Now the number over languages, the number of languages over sigma is the number of subsets, right? So the number of subsets is actually uncountably infinite. So I actually can't count those subsets here. All right, so what that means for us, right, what we want to get from that is as we move on to section 3.4, there are only a countable number of deterministic finite automation since each has a finite description, but there are uncountably many languages. All right, so what that means is that most languages cannot be recognized by any DFA at all. All right. So again, right here, what we want to get from this section is our basic kind of a vocab here is we have an alphabet. Right, string, right, the empty string, epsilon, and then E star, the set of all strings over the alphabet, right, and that is what gives us our language. All right, and again, language in a mathematical object sense, right? That's what we're talking about here.